Now you can share, Claudia. Carla, please.
Yes. Okay, you can see my slides, right?
Yes, I see them.
Yes, we can see your slides and we can hear you. So
Okay.
the final speaker for this morning session is Carla Bonifazi from Universidad Federal de Río and the Institute of Advanced Studies in Buenos Aires. And she will talk about, well, you can see the title, and I guess this is about the CONI experiment. So
yes. Thank you. Yes, I will talk about detecting coherent elastic neutrino-nucleus scatterings. Of course, I will focus more on CONI, but I just review a little the state of the art on sevens. So I will call sevens. That is how we like to call to the interaction. This interaction is a process where the neutrino will scatter with the nucleus. The nucleus will recoil as a unit particle, so we will not see any interaction with what is inside the nucleus. So that's why it's elastic and coherent. So this interaction was predicted 40 years ago, a little more than that. It's an interaction that we expect from the standard model, but it took very long to measure for the first time. This was in 2017 by the coherent collaboration. This experiment, I will talk a little more about this, but it's an experiment that is running in a spallation neutron source. So it's a beam experiment somehow. So this process is dominant for the very low energy, let's say below 50 MeV for medium mass of the target. So it's on the other side of the scale that the people is used to. So the interesting of this interaction is that thanks to the coherent elastic, we have an enhancement on the cross section. So the cross sections increase with the square of the number of the neutrons on the nucleus. So if we take this into account, we can see by comparing with the most normal interaction that we are used in neutrinos experiment, that is the inverse of beta decay, we can see that we gain at least 2 orders of magnitude. So this allows us not to need huge detectors for detecting the sevens. We can have a detector at the scale of the kilograms or less. And the other interesting point is that it has not a threshold on energy, so we can go to much lower neutrino energy and explore better the neutrinos from reactors. So, but there's a price that we have to pay for that. That is that this recoil is very, very small, very tiny. So that's why it's very difficult to be detected. And this is why it took more than 40 years for the first detection. Now this is possible because in the last 20 years, we were developing as a community a lot of low background detectors, low background and low threshold detectors because of the dark matter searches. So now we have the expertise also to explore the sevens. What is interesting is if you see in the community, you have the experience goes by pairs. You have one dark matter detector and the same technology for the nuclear the nucleus recoil. For us also, Connie has his dark matter experiment also. Why is important to detect sevens? The reasons are a lot of. One of the main reason, and that was putting a lot of interest to the collaboration, was that the neutrinos are going to be a floor for the dark matter experiments, and our experiments on dark matter are more and more sensitive. So we are soon going to detect neutrinos by 7th on those detectors. So it's important to understand and to characterize in each type of detector this interaction. Also, it's interesting because it's a prediction of the standard model. We by measuring 7s, we can get precision measures of the cross sections and explore also values as the Weinberg angle, and also we have a lot of possibilities at physics beyond the standard model. So I will not go in details. There's a lot of experts here that can explain much better than me, but just for completeness, I make a list with some reference. So if people is interested in that, they can go to the slide and give a look at the reference. But is very interesting because it's a very nice channel to access to this beyond standard model physics. Also, there's a lot of interesting concerning the nuclear physics, because accessing to the sievings and studying the interaction, we can study nuclear form factor when the energy is not too small. And also we can study the neutron distribution radius, that is not as much easier to get this information as for the protons in the nucleus. So there are some works done by people from the coherent data that are very, very interesting. Also, we can detect supernova neutrino from using the sieving interaction. So for that, we need huge detectors, not as small as for the detection in the facilities, but it's a way just to detect. And what is interesting is this 7th does not depend on the flavor of the neutrino. So also this is interesting. And also by modeling and studying the interaction, we can get much better models for the supernova energy transport of the model that we have. And finally, other application that is getting more importance now is just to monitor reactors, nuclear reactors by the 7th, and also to use for application of no proliferation. Which are the sources that we have to study 7th? We have two kinds of sources, and what we want is that the source has a high flux on the neutrinos, that we can model or understand the production of these neutrinos. We want to have environments where we can sit our detectors that have very low background rates, because it's not an easy detection, and also detectors that will allow us to detect the multiple flavors. And sources producing multiple flavors. So we have two kinds. That one is the neutrinos coming from stopped pion beams. In those accelerators, the pion will decay at the rest, and then we will have the neutrino from the mu neutrino that will be produced as the prompt, coming directly from the pi decay, and the energy will be around it's a monochromatic neutrino flux with an energy near to 30 MeV. And then from the decay of the muons, we will have the electron neutrino and the anti-muon neutrino that will have a more broad spectrum. On the other hand, we have the nuclear reactors that are complementary, because those reactors produce anti-electron neutrino that cannot be produced by the beam. This is mainly as are produced by beta decay in the fissions of the fragment. We have 4 components that are very well understood, that can produce this flux of neutrinos that we can see in this plot. And then also we have the neutrinos coming from the neutron capture from the uranium in the reactors. So the energy is much lower, and is near, the maximum is around 1 MeV. We can sit our detectors in environments with clean background and reduce the cosmic background by active and passive shift. The disadvantage that working with a nuclear reactor, the main disadvantage, let's say, is that we cannot synchronize our flux of the neutrinos with the experiment as it is in the accelerator. So this is a problem because it's a more passive detection in somehow. So if we see how the experiment or the next future experiment are distributed around the world, we can see that there's a lot of interest in and a lot of people are putting effort. And as I said before, each experiment more or less have one pair that is dedicated to the dark matter searches. In the South American, we have CONI that is seated in Angra, and we are pushing for another experiment, the next generation experiment that is Violeta, that could be placed in Argentina. So going a little more to this spallation neutron sources, we can see here how the spectrum, the distribution of the neutrino production is, and this in this plot we can see the neutrinos as a function of the time of arrival from the beam, and in this particular spallation neutron source, the coherent experiment installs several kinds of detections in one corridor that is what they call the neutrino area. So they see different technologies, detectors. Some of them are built in built situation, others were already removed. But the important point is that in 2017, with one of the detectors, they were able to detect for the same time this coherent scattering. This was with this ionized cesium solid detector, scintillator, with almost 15 kilograms. Here we can see a picture of the detector. This detector was placed around 20 meters of the source, and they got a almost 7 sigma significance detection. So it was very exciting and very nice results. And then they continue running for more time. Now is decommissioned. In 2020, they published really a good confirmation of the detection at 12 sigma, what is very consistent with the previous measure. And also the result that they have is consistent with the standard model prediction at 1 sigma. And also they got better in the data analysis, and they were able to lower very significantly the systematic uncertainty. One of the problems of this kind of detection is that we are measuring nuclear recoils. For that, we need to know the efficiency on the ionization production. This is what we call the quenching factor. Since those energies are very low, we used not to have information data from how much is the quenching factor for those energies. So also in parallel to all these detection techniques, several efforts on the measure for the different materials at different energies. The quenching factor is being done by the community. And also some new models were developed, and that's why they were able to get much better systematics, because now the uncertainty related to the quenching factor is below 5%, what is very, very nice for those experiments. And then also, since they have another detectors, they were able to see sevens with, this was the second of the sevens, was the second measure with argon, with a liquid argon detector that is near at the beginning of the neutrino corridor. This detector has 24 kilograms and is at a distance of 28 meters from the source. It's a single phase detector, and they detect 7 with a 3 sigma significance. And what is very nice is that for the first time they could see experimentally the dependence of the cross section with the number of neutrons on the target. So now we have 2 experimental points, and they are planning to get data with this germanium detector and also with other detectors that they are installed. So this plot will be much public with experimental data soon. Going to the nuclear reactors, another detector that is very, very nice and promising is a CONUS, that is a detector that is installed in a nuclear reactor in Germany. And it's the same model of the nuclear reactor that is built in Brazil. So CONUS and CONIC have the same kind of reactor. And it's a 4 gigawatt reactor, one of the most powerful reactors. And they were able to install 4 kilograms of hyper pure German detector inside of the reactor in this position to 17 meters. And the experiment is very, very nice. I like it a lot. And they are running with a passive shield and active shield for muon rejection. And thanks that they have this possibility to have timing resolution, they are able to reduce significantly the background. So this is very nice. The background level at the experiment is very, very good. And also they are able not to see the reactor. That means that the background does not change with the reactor periods. Those experiments that use reactors need to, for the data analysis, the approach is to do reactor on minus reactor off data. So the reactors normally used to have 1 month of maintenance each 12-14 months. And at that moment is when the background can be measured. So all those measures also are limited by this background determination. The energy threshold, because of the kind of the detector that they are using, is 300 eV. It's low, but it's not too much low, but it's good for 7th detection. So with the data that they took, they did this analysis that is reactor on minus reactor off, and they did not see any signals, but they were able to set upper limits with the 19% confidence level, and they were exploring this the evolution of these upper limits with the value of this quenching factor that is the uncertainty point for those experiments now. And the data that they got is not compatible with quenching factor before above 0.27. So this is an unexpected result, and new measures were done for these detectors. There are 3 or 4 experiments running using these hyper pure German detectors, and the quenching factor is around 17.20. So the good point or the advantage of this experiment is that the reactor will shut down forever at the end of this year. So they will have a 1-year campaign for background measure, and this is going to be all 2022. So after that, we expect very nice results. The people at CONUS are very confident on that. So this is our experiment that is in South America. This is the CONI experiment for coherent neutrino-nucleus interaction experiment. Is seated at 30 meters of the core of the nuclear reactor in Angra 2, that is 4 giga, the same reactor that Conus, in this shipping container here. And in the container, we share the space with another experiment that is the Angra Neutrino project. We have a lot of synergy on the infrastructure and all the difficulties that are to run an experiment that is far away and not in lab conditions. So in this detector, since we are using not time resolution detectors, the shield that we have is a passive shield. And CONI is an international collaboration, mostly from countries from South America, with a lot of Latin American participants in the US. So this is a picture of the experiment when we open it once for maintenance or for changing the CCD. So here we can see the components, the 2 layers of the polyethylene, plus the 15 centimeters of lead. Then we can see here the electronics, just to keep the signal from inside of the DWAR, where we hold the vacuum. We have the cryogenic of the detectors. To this vacuum interface voice is just to pass from inside the detector to the readout and electronic that is behind the experiment. We cannot see in the picture. So if we see what is inside, we can see here a copper box with several CCDs installed. Each line is 1 CCD. We have 14 installs, and those are normal CCDs with 4 key by 4 key pixels. So these CCDs have a pixel size of 15 micron each, and a thickness of 675 microns that are very thicker CCD, because we are using for particle detection and not for optics. With a total mass of 6 grams each detector. And those detectors were developed by Berkeley and Fermilab, that is the lab that make the packaging of the CCD, have a good relationship and develop agreement with people from LBNL. They are continuously developing new detectors. So how those detector works is when we have the interaction of, let's say, a neutrino, but it could be a dark matter that interacts with the silicium nucleus will recoil, and this will produce ionization. So we have here a voltage difference, so the electron and the holes will not recombine, and in our case, the holes will be storage at the gates in the top of the CCD. So the advantage of those detectors is the target is the detector itself, so the interaction is happening inside the detector, have very, very low threshold and an excellent spatial resolution. But the problem is, again, we don't know the quenching factor for silicium at those energies. Or the knowledge that we have is not enough. We know much better now. And also that this energy, the recoil, the deposit recoil energy is very, very small. So it's very difficult to do the detection. So once the charge are in the top of the CCDs, where we have the gates and we accumulate the charge there, we do the readout of this, and the readout is done pixel by pixel. What we do, we move the charge to the sense node where we have the amplifier and where we do the readout. So this is the key point to reach this very low energy threshold. Here in this picture, we can see, this is a real picture from CONI. 3 hours exposure is a small part of the CCD. The CCD has a total 6 centimeters long. Here we can see the different kind of particles. What we look for is a recoil signal, is what we call a diffusion hit, that is a very tiny detection. And also some low energy electrons can mimic that, or a combination of the fluctuation of the readout noise with the dark current can mimic that. So this is the why it's difficult the detection and challenge, very challenge the detection. Here we can see that we don't have only a spatial resolution in X and Y, and also we are able to have a 3D reconstruction of the event, because the charge, when are going to the gates, will diffuse, and the charge that will diffuse will allows us, after calibration, to know where the interaction was happening. We use the muons that cross the CCD without any problems to do the calibration, and then we have this charge calibration, and we are able also to know where the interaction happened, and this allows us to put some fiducial cuts on the event selection for getting a much better background. Talking about the readout noise, we can see where we don't have any events. We can look at the fluctuation of the values on the pixels, and we can see that the readout noise that we have is less than 2 electrons. This is enough, but we will see that it's not as much enough as we want. So here we have some results of CONI. These first are the results with the run that we performed in 2016 to 18. We need to join those years because in the 17 we did not have reactor off. And here we can see that we were able to put a limit on the detection at 40 times the standard model. This was 95% confidence level. If we compare with the more realistic quenching factor that we know for the moment, that are the measures done at Chicago by Chavarria and others. We did not detect yet the coherent scattering, but this was enough just to get the best limit on some extensions of the standard model, and this allows us to show what competitive can be a reactor's detection of these sevens. So now what we did with this limit, we set the limit for the light vector mediator and for the light scalar mediators, and we can see that in blue we have the limits got by the detection of coherence, and in orange and red we can see with the two quenching factor models the limits setting by CONI. Those limits are very close. Also, CONUS have now very close limit to ours. So what we need is to get much better relation between signals to noise, and since we could not at the time change anything of the detectors or going closer to the reactor or whatever, what we decided to do was just to work not in a normal acquisition that is a one-by-one data taking, but we binned our data in 5x1 in order to increase the signal, as a consequence, the ratio. So by doing that, we were able to improve on the efficiency, on the acceptance at the lowest energy, and also we learned more about the detectors, and we were able to get a much better pattern recognition or reject background sources. So here I have this very technical, but I have a few examples. Then first, we were able to perform a much better size depth calibration. With that, we were able to understand the contribution of some events coming from the backside of the CCD that are produced in a layer of the CCD that has not a very good charge collection, because we have some kind of recombination of the ionization of the pair electron hole pair, and because of that we have at the lowest energy contamination. So now we reject those events coming from the back of the CCD. And with that, we are able to reduce the background of our experiment. What we did for the data analysis, it was a blind data analysis. So we freeze and we study of the characteristics with one of the reactor off data sets. One, we were fine with that, and we were happy on the analysis that we had. We check the stability on the set on the reactor on, but for that we were using only high energy events above 1 keV. And once we were showing that the data was stable, because if we want to do the subtraction, we need to have very stable data, we unblind and we perform the analysis in the region of interest. So this is what we have. And we don't detect any signal yet. We confirm the limits that we had. Now there's in the literature a model for the quenching factor that allows us to go to the lowest energy, because with this analysis we were able also to low a little more the energy. Now our threshold is in 50 eV, before it was 75. With that, we can show that we are 34 times the standard model. This is just a paper that is in the archive since some weeks. So this is a rather new result. But again, the limitation is again, or we lower the background, or we lower the threshold, or we enlarge the flux, or we enlarge the mass. Or we do the 4 things at the same time, that would be great. So for the moment, what we can do is to go to much lower ratio, to go to 15 eV, and this is with the new technology that is a skipper CCD that was mentioned before, and is how some dark matter experiment with CCD are operating or will do soon. And this detector is almost the same detector, but have the characteristic that when we put the charge in the sense node, when we are reading it, we do not destroy the charge. So that means that we can read the charge as much times as we want. And this is what we do. So we put the charge of 1 pixel in the sense node, we read it, then we push back the charge, and then we push the same charge again, and we read n times. So here in those pictures, it shows the capability of the skipper CCDs. In the first column, you can see that we have 1 electron somewhere, but due to the readout noise that is 3.5 electrons, we cannot see the electron, we cannot resolve the electrons. But if we perform 4,000 times the measure and then we average, we get a reduction that goes with the square root of the number of times that we read, and we get a very subelectronic noise, and we are able to measure the electron. This is really very interesting technology that opened the door to a lot of other things, and also to quantum science detectors. Are great detectors, I like a lot. And here we can see that the sigmas drops with as expected with the square root of the number of samples, and the price that we pay for that is that we are much slow detectors, because it takes more time for reading all the sensors. So we are putting some efforts on that, and we have some techniques as binning and other things just not to take so long. And we are taking data with those experiment detectors normally continuously. So these electrons counting goes up to any energy. It's not that we count electrons when we have 1 or 2 electrons. We count electrons when we have 1,550 electrons, as in the iron peak. For example, if we put this source, we can see here that we resolve the number of the electrons. So this is very nice, and the Sensei experiment for that matter have also very nice result. You can check in these 2 publications. So what we did in CONI, just was in July this year, we installed 2 skipper CCDs to characterize the background and the performance of those detectors at sea level, because at sea level always is much difficult because of the atmospheric background. So we have to redesign part of the detectors. Also, we changed the electronic with electronic that was developed by people from Fermilab, Bahia Blanca, dedicated to these skipper CCDs. And here we can see again our copper box with the 14 CCDs plus the 2 skipper that we installed. That, by the way, since we were talking about this before, the one that the DM square hubs is exactly the same. So as I say, always we have one neutrino experiment and one dark matter experiment going together. So this is not too large detectors, but are enough for background characterization and for first measurement and for the final design for an upgrade. So here are some preliminary results of the last month where we were running. So we decided, just for the background characterization, we decided to run in 3 steps. First, we were running something a little more than a month with no shield, with the experiment open. Then we partially closed the shield with only 5 centimeters of lead, the inner polyethylene, because we could not close in another way. And today, my colleagues just finished to close completing the detector. So they finished before my talk starts. And here we can see some images, very nice images with the particles. I like this because it has the huge electrons going there. Then we can see that the readout node is very small. We are in 0.15 electrons with very stable performance. And this is the evolution of the single electron events, mainly coming from the dark current or coming from some spurious charge that we can generate in the moment where we are moving the charge. But it's also very stable. So this decays normally that this happens when we start to take data in a run and then stabilize. So the values are very good too. And here for comparison, we don't have too much statistics, but for comparison, we put the efficiency for the standard CONI that is in black, that is the experiment that we were running until the end of last year. And the new efficiency with the skipper CCDs, and we can see that we can go further in the lower energy, and also that the efficiency is much higher. So that is also very, very nice. So with the data that we took with the partial shield and without shielding, we were able to perform some preliminary background spectrum. So the rate here is in DRU, that is events per kilogram per day per kilo electron volt. And here we can see in open cycles are the data without any event selection, and closed full cycles are the data with event selection. In blue is without a shield, and in red is with a shield. So I think that what interesting the most is the red dots. And we can see that if compare this red dot with the background of CONI, that is the best background that we reached, that it was in 2019, we can see that we already are competitive with a standard CONI when the shield was not completely closed. So let's see what we have in the next month. So this is very promising, because this means that also with the skipper, we are able to reduce things. We are able to put much better selection, data selection cuts, a much lower detection background in the experiment, what is very nice. So that means that we don't lower only the threshold, but also we are able to lower the background, remaining at the same position. So just to finish, I want to to talk a little about the seventh detection, that is a very active field. We are having a very exciting moment because experiments are running. It's very promising. We have some experiment that will be able to get the measures soon. And also we got a lot of knowledge on the technique, on the detectors, on the background. So we are able to do the design of the next generation detectors. And also there's a lot of synergy between the experimentalists and the guys that are doing the theory, and this is very, very nice. Going to CONI and to the CCDs are very promising technology. For the moment, the spectrum is very flat and very nice at the low energy, what is very nice. Also with the standard CONI, we were able to demonstrate that we are competitive for BSM physics, and with the data that we already acquired, we got a much better sensitivity, and already we have the 2020 data to analyze that will give more statistics, and we are working on that. And now we are working on that, but also using the knowledge that we have from this background and detector with the skipper, just to analyze the 2020 data, what is very, very nice, also this energy. Then just to finish, skipper is the future. We want to have more mass skipper detectors, but we need also to finish the characterization of the response of those sensors at sea level, and see which kind of detector we can design to get the best. We are planning in CONI, once we finish this campaign of background measurements, to increase the mass. We wanted to install something like 50 grams skipper CCD at the position that we have, but we are already discussing with people at ANGRA in order to install a prototype at in the same position where CONUS is, at 17 meters from the core. This position has an extra shield for background, cosmic background, sorry, because it's below the pool where the used fuel stays for decay. So this position is very promising. And also recently, I think 1 month ago or something like that, the Violeta collaboration installed a skipper CCD at 12 meters of the nucleus of the Atucha 2, that is a reactor of 2 gigawatts. And also this is very promising, and for sure we will work together, CONI and Violeta, in order to get the best information we can have from those sensors in order to have the next generation detectors. That's all. Thank you.
Okay, thank you very much, Carla, for this enlightening talk. And if there are questions, we still have a few minutes left for questions. I see Diego.
Thank you, Carla, for a nice talk. I was wondering if with the skipper CCD technology, we will be able to really measure the sevens at the level of the standard model.
It's clear that what we learned from CONI standard is that we need a much larger detector, because the background was as much as we expect. This is the reality. But with the skipper, since we moved from 50 eV to 15 EV, we lower the threshold, you increase the number of events, because this goes like that. So that means that with a reasonable mass, let's say between 50 grams and 100 grams, and a year of data or something like that, you should be able to measure sevens. Yes. The other point is to go near to the detector. That's why there's a skipper in in a touch for characterization. But when you go near to the reactor, the problem is that you have the background of the reactor. So you need to understand very well the background coming from the reactor, shield your detector from it, and then perform the solution. So we will see what is much better and where to place the next detector for that.
Any other question? I don't see other questions. Yes. So I have also a simple question. And this, the nucleus, then you are using the target, which is, can you say again, you only have one type of target in this experiment?
Yes, that's silicon.
Silicon. And can you change? I mean, are there any, these skippers are all CDD skippers, they are only silicon?
Yes, there's only silicon. I know, but not too much, that some groups try to develop a germanium CCD, but they have some difficulties. The performance of those detectors are not in a shape that could be used for detection. If you want to go to another target, you need to change the technology.
Like in this coherent.
The detector. Yeah, like germanium with hyper pure germanium detectors or some other scintillators, as the other experiments are doing.
Questions for Carla? Claudio?
Yeah, Carla, where, well, very nice talk, actually. Where do they build the skipper CTDs?
The skipper are designed by Berkeley, and then they send the design to a company. The company, I don't remember the names of the company in the US, but I know that the normal company that was producing the CCDs say that they will stop to produce those CCDs. So people from Fermilab, BNL, are developing another provider. One is a microchip, and now the first detectors built by microchip are being tested in Fermilab. So this is nice because now this opened 2 or 3 companies that can build a detector will start to produce some skippers, and we will see the different performance. The technology is the same, right? But then you have the production that can change some things. The first data from the microchip that some detectors were already tested, packaged at Fermilab and tested, are very promising. We have a nice, we can do a skipping, for example, and see signals in the detector. So we are now learning how to get the best performance of those detectors.
Yeah.
I see another question by Ibrahim.
Yeah, hi. When do you plan to measure the electromagnetic properties of neutrino, like magnetic moments or charge radii neutrino?
Yes, this is possible, but for that, we with the data that we have, we are not competitive for putting some limits on that. So we need to be much closer or to the standard model or to get the measure in order to the sevens in order to start to study those properties. Also with the skippers, what we can do is to measure, since the threshold is very low, you can see the interaction between the neutrino and the electron, not the nuclear recoil, right? So also this will be able to reach this kind of interaction that has not the problem of the quenching factor. It's much difficult to detect it because it's much lower energy, but we will access to that.
Thanks.
Okay, I don't see any other questions. I think Edgar or Rogerio, if you have some announcement.
We need to take the picture.